Good afternoon. My name is Jamie Q. I'm the Dean of Engineering School, just in case you don't know me. It's my great pleasure to welcome all of you to this Engineering Dean's Lecture. The Engineering Dean's Lecture series was established to honor an individual who has played major leadership roles in and has made significant contributions to society through working in areas related to engineering and technology. That's one sentence. The speaker today best epitomizes the lecture series, what the lecture series stands for. Mr. Keith Moore is an HP Fellow and Vice President of R&D at HP Labs. In case you don't know what HP stands for, how many of you don't know? Everybody knows. For those of you who will have a chance to go to Palo Alto, you should make a point to stop by an old garage where Hewlett and Packard started their company. On the street, there is actually a plaque on the sidewalk, and on the side there's a board that tells you what this place is. But unfortunately, you can't really see the garage because it's behind a private house.
If you do something significant, we'll get you to see the garage.
All right. But if you do visit Keith, you will be able to see their offices in the lab, and they kept the original style and furniture and everything. So, all right, let me continue. Keith has extensive background in R&D, is both an inventor with more than 35 patents, and as a line manager, bring inventions to market. His inventions have been implemented in almost all HP LaserJet and commercial printing products. In his current role, Keith leads the print adjacencies and the 3D lab, where he and his team develop and research the underlying material science and microfluidic for HP's polymer and metal 3D printing technologies. Prior to his current role, Keith was VP of R&D for all of HP's LaserJet and INKJET softwares, including drivers, management softwares, and third-party solutions. According to Keith, his favorite part of being at HP Labs is the ability to see the future and to bring that future to market. Just to pair that up, my favorite part of being at Tufts is the ability to go around, find the jumbo, and bring that jumbo back to campus to give the dean's lecture. Today, that jumbo is Keith. Keith received his Bachelor of Science in Electrical Engineering from Tufts University in 1985. Afterwards, he went on to earn his master's degree in computer science from Stanford University. We won't hold any grudge against that, Keith.
I knew that was coming.
Without further ado, please join me in welcoming Mr. Keith Moore.
Hi, everyone. So from a logistics standpoint, I think I have to come over and click a button, right? There's no clicker, just checking. Okay.
You just wave like this.
Yeah. So, it is true that I think I can absolutely predict the future. I just can't tell you what year it'll be in. So it is amazing what you get to work on, and a lot of times ideas that kind of pause. Too dark. I don't think they can now they can see me, right? I'll do shadows. There we go. Hopefully you'll be able to see the pictures. So the comment is, yeah, I definitely can maybe see the future. I just can't tell you what year it'll be in. Let me walk into a bit about 3D and additive manufacturing. I have had both HP Laboratories started over 75 years ago in Palo Alto. It's where Bill and Dave put their offices. It is an applied research laboratory, and if you wonder what the heck the difference is, it means about Maybe 30% of our work is very similar to the academic work you might do here. The other 70% is aimed at making money. And now how we make money might be it comes out as a product. It might also come out as a new business creation or licensing of technology, which also some people here will probably run into. I had a couple of quick questions. How many people are undergraduates? Okay. How many are graduates? How many are professors or things of that nature? Okay, that's a good mix. All righty. So this is one of my favorite quotes. It's true disruption is indistinguishable from a distraction in its infancy. And the reason I bring this up is all those professors will know what I'm talking about. You will have done something pretty fundamental, and then years later it has changed the world. But anyone guess what this is?
INKJET.
Really?
Ink drop.
You think it's an ink drop? That's a pretty good guess, actually. It is, in fact. That's pretty good. It's the lower spot of the P from 1982, and this was a quote from the guy who was the general manager for HP INKJET in 1987. He was talking about the first product, which was in 1984, which was this little ThinkJet thing. Now, most of you aren't old enough, probably, to have seen this thing, but why I want to bring it up is there's another Moore's Law. I'll say it's Keith Moore's Law. But it doubled, the speed of our printer has doubled every 2 years for the last 30 years. And why I want to bring that to market, oh, let's see. Someone here might be not used to logarithmic scales. That's what it looks like, is when you have doubling happening every 2 years, it ramps like crazy when you're out here. Now, when you're on an exponential, it's very difficult to see what's happening. But the reason I want to bring it up is most people started to understand what was going on with ThinkJet or INKJET technology roughly about here in 2000. Because it started to ramp enough that they could see what that was doing to the industry itself. So now we're putting out print heads like this. They will put out a press which will do about 800 feet per minute of printed material. That's on the order of 40 pages per second. And if you just think of that from every drop going down is a bit, and you think about the flow rates you're dealing with, you're in terabytes of data flowing per second, flowing across this system. So it's an amazing amount of systems when you're running them. Anyone who loves GPUs, you cannot believe how much we are cooking out the back end of these when we're doing our large presses. The reason I wanted to talk about INKJET was that if you think about where the company was in 1975, and roughly when I joined, which is 1985, if you look at what's going on here, I entered right about here, and we were an instrument company, and we're trying to convince the founders to go into this great new thing called a printing company. How do you think that went?
They probably looked at you like with a blank stare, or they kind of had like a laughing.
They were sitting there going, well, what are you going to do with it? And we have these things, we didn't even call them computers, we called them controllers at the time. My reason for bringing this up is that printers were an adjacency to the controller business. They were ways to get your mass spectrometer, your gas chromatograph, or your oscilloscope to have a trace dump, and then you got a plot out of it, because cut and paste in those days was cut and paste. You literally cut it out and paste it into your document. That's where it came from. But in 1995, the same thing happened again, which is we introduced what was called PA RISC, and for those of you who are computer engineering, this was precision architecture, RISC versus CISC processing that largely came out of HP with Joel Birnbaum. 2005, we introduced commercial printing, which was this whole notion of everything you see, packages, signage, building wraps, buses, anything that, that is basically printed, we brought those in. And each time we're trying to convince the company to take another step, to take on something it didn't do before. So you can probably guess what the next one is. It's 3D. All right. Now there's one after this. I'd love to tell you about, because I got to see a whole bunch of stuff in certain people's labs today, which was great. I'll come back to that. But if you come back to this space, HP Labs' role is to be in front of these. So we invented thermal inkjet in 1978. We invented PA RISC in 1985. We invented the latex inks in 1995. And we have these things called jettable agents. So I'm going to talk about what jettable agents are and how they relate to all the stuff you see on the table in just a moment. But the core of this is often it's half a decade to a decade that you're doing the invention before you'll see it in market, even in industrial research. All right? So don't lose hope when you have your thing going and no one's paying it a lot of attention at the beginning. It does change. It just takes a moment to create that spark that changes the world. Exponentials are tough to live in. So one of my favorite quotes, if you're a baseball fan, predictions are hard, especially when they're about the future. I like that one a lot. Another one is the best way to predict the future is to invent it. This was Alan Kay's quote. He's also an HP fellow. Anyone guess what this is? And the person who said blob of inkjet is not right. Actually, they're partially right. That thing we did in 2010, and my boss said, "Why are you so excited?" Yeah, it doesn't look like much, does it? Okay, 6 years later, we came out with this part. So I'll hand this around. This is a brace, but the point was we went from a blob of plastic that we had figured out finally how to melt consistently, how to jet a small amount of fluid down onto the plastic, and the fluid basically changed the thermal properties of the absorption of the polymer so that when we heat it with a lamp, it heated and the stuff around it didn't, and that blob that went down could now be replicated to make this. Okay, now 3D printing's been around for a while. Why are we so excited? Do you remember that Moore's law? Do you remember this notion of the head moving across the bed? Do you know how many drops we put down per second that we can do all this in parallel? If you have a laser going around doing stuff, that's like a CPU. This stuff is a GPU, a graphics processing unit. We do it all in parallel. So the speed performance is what suddenly happened, is this stuff is now 10 times stronger than what was on the market, 10 times faster, and it turns out 10 times cheaper because everything we don't touch, it's like cookie dough, anything we don't print on can be recycled into the next batch. You can just cut the cookies out, put the next batch in. I'm going to show you how this works, but I do hope someone will ask me a question, and I'll give you a motivation for this. I might give you something if you ask a question, if it's a good one. I get to judge what's good. So in 2018, we came out with color. So if you think about 1985 with the ThinkJet, we then came out with the ColorJet. We are following in 3D exactly what happened in 2D. I can watch the trajectory. I can almost tell you now the dates when things will show up, because it's only a small matter of physics and chemistry and a ton of engineering and a little bit of other stuff to get stuff to come out, and a bit of luck. I will actually add that one in too. We just announced, and 2019 is on here. Don't get me in trouble, but it's 2019 because they actually announced it for 2019. But the first one came out where Meg Whitman, who was our CEO at the time, said, "We're going to have a 3D printer." And we're like, "You're going to what?" Because we weren't ready. There's a big difference between running the experiment and having something you can ship to people. So we're at the point where we have the parts and we're printing them in-house. But it's a ways to do before you ship it to people. You know how to do the safety conversations and everything else. We are a powder-based system. Anyone know the difference between metal powders and fireworks?
Metal, say that again?
Metal powders and fireworks. You can, they're pretty much the same. There's gunpowder in one. But But yeah, so the explosive capability are some of the things we absolutely had to figure out and how to handle that, especially when you're working in small micron-based powders. Okay? So what's fundamentally changed about 3D since probably the time you're working with it or what you're hearing? Essentially, all that stuff that was like Dremel printers, little walk-arounds, even the SLS stuff, that was mostly aimed at prototyping, right? Mostly doing, something where, oh, okay, I got some device, it looks good. What's changed is we're now doing production. This is one of our printers. This is actually a line of printers. Customers don't buy one. They buy 2, 4, 8. Actually do seem to be counting a binary. But they actually do, and I'll show you a little bit about what's happening with the printers right now, but this would be a manufacturing floor, and instead of having one large press or a large injected molded plastic machine, they're making all their parts this way. And that manifold I'm setting around, and if anyone could guess what it was, that's for an electric vehicle. That's the water cooling for a battery. That's what's in there. What's fundamentally happening is the parts are good enough. I won't say they're exquisite, but they're pretty darn good. I'm happy to go through all the tensile strengths. It's as strong as the underlying material. Because we don't add a glue, we actually melt it to the layer below. We actually fuse the layers together, so it's actually the underlying material when we're done. We work primarily in, for those who care, semi-crystalline materials. We're not doing amorphous. We will someday if I can get that lab experiment to work. I'll show you a little bit about how the system works, and I hope you'll also ask me about it. So this is what HP ships. We ship a printer. We ship a trolley. The trolley rolls into the printer, and if you've ever seen those cooking shows where they seem to roll one out, you have one coming out, you put another one in. It's a manufacturing environment, so they're going to have a trolley come out, and they'll put another trolley in, and it'll start printing the next batch. So everything's always moving, and there's back here a cleaning station. I'll show you a little bit about what that looks like. Now, I didn't want to do any marketing videos or anything else, but I chose one small section from a video just to show you how this stuff works, because they actually say it a little better than I can. But when you have a press like this, here's what's in the trolley. The stuff that comes out the trolley, this is 2 batches of the trolley. I have them color-coded just so I could tell which was in which batch. All of those parts came out of that trolley. So when you're printing with this type of system, you're filling the whole volume, and now you're packing all those pieces together. And anyone who wants a lovely computer science problem, try and pack all these parts. It's like 3D Tetris, but all the parts are different sizes, and you don't know too much about them. And oh, by the way, they're thermally coupled, so when they're near each other, thin parts are okay next to thin parts next to fat parts aren't okay, and anyone who wants to do large body problems, all sorts of nice thermal issues show up when you're trying to pack parts next to each other and get higher yield. But this is kind of what the parts look like. I have a bunch of them up here. I'm happy for you to look at them. But that part packing algorithm, you have in software, you're taking all these individual CAD files and you're trying to gang them all together so that they can fit within this production run. And this turns out to be where all the cost is in a manufacturing system. So when you think about manufacturing, it's about yield and reliability and quality. So we will pack all the parts in there. Lovely algorithm problem, but I wanted to show you how it works.
The process begins by applying a layer of material in a work area. Then, in one continuous pass, we print liquid agents across the full working area using HP thermal inkjet arrays. In the opposite direction, we combine the layering and energy fusing into one continuous pass. This HP proprietary architecture using HP's thermal inkjet arrays is capable of printing 30 million drops per second along every single inch of bed width.
So in that particular video, what's happening is we're jetting out essentially a black dye, you can think of it that way, that absorbs in the infrared. It'll just melt to the layer below it when we apply the heat. So you can think of it as we lay out a sheet of powder, like a piece of paper. We jet onto it where we want it to print. We hit it with a lamp, it fuses. We lay out a sheet of powder, we jet onto it where we want it to print, and we just keep going. So those typical things about support of 3D, if you have something that's got a kind of a long edge to it, if it was packed in like this, you don't have to have supports for it anymore. because the powder itself supports the material that you're printing. It also means that we can run super, super fast because everything's done in parallel. Z-axis, meaning going up, turns out to be the slow part. And I guess I'll look around and see if anyone has done their semicrystalline base melting points and recrystallization points. What might limit us in Z?
Resolution.
Cooling and resolution. It's absolutely that. So what happens is for your strength of the material happens because you've come through the cooling cycle long enough. So if you don't control the cooling cycle and you don't control that melt to recrystallization point, which is what, when people use a laser to go around, they just make a pool of plastic. You have to control the heat through that whole space. So we actually use two agents, one called a detailing agent and one called a fusing agent. The detailing agent is a cooling agent. Now for those who are working on heat transfer, lovely, hard problem. We keep putting heat in and then we put in water and then we get rid of that water. It's not the most thermally efficient thing to do. So there's lots of room for opportunity in this space.
I assume you're talking about thermosetting.
Yes, that's exactly right.
agents.
Yep. But in our particular case, because we're not actually using a glue, so we don't do any gluing or anything else. It's just the underlying polymer itself and how that will recrystallize. So I did a little home video. I went down to my lab, and I want to see if anyone can guess what this thing is. No? I went downstairs. I actually couldn't believe this was going, and so I'm looking, what is that thing? This is it actually printing. So I back up, go over to the control panel. It's Thor's hammer. And you can't believe. And the guy was also printing a bunch of other stuff, which was, I think, his tableware and maybe, so it comes out like this. So when you reach into the vat or into this trolley, the parts come out and they're a little dusty. So we use these incredibly fine architected tools. They look like brushes to dust them off. So kind of architectural tools. I did want to mention that all that powder is basically put back into a container. It's a giant vacuum cleaner. And then you take the powder from that and you just use it in the next batch. So we tend to mix it 80-20. So 80% old powder, 20% virgin powder.
How do you eliminate contamination?
We don't have any because we're spraying with such precision of picoliters going down that we're not touching anything else. So we know what we've printed on, and the places we print turn out to, to be fused. So as long as you're fusing, you don't have this blending. Now there is a final piece, which is right on that edge effect, depending on what question you want to ask. Those things come out like a potato, so there's a little bit of a residual around it, and we do treat that powder slightly differently. But because of the packing density, we don't have that issue. And it's a great question. So here's Thor's hammer. I want to bring a picture of Anthony holding this thing. It's actually really heavy because it's solid through and through, and it is quite heavy. But I wanted to show you something else. If you can go, he was doing it to show how strong the parts were, yeah. And sometimes I throw that part around, just the one that's going around. I think he wanted it for his Halloween costume. But I want to show you this one, which is, look at this. Okay, that is the same material as this. What changed? Is that cool? I think it's so cool. So what I said to you before was that we can jet out a black pigment onto the material, and just like your asphalt or anything else, it gets hot. You know, white one might be a lot cooler. So we have that temperature differentiation, but if I can jet out a pigment, and I can control it in, let's call it 20 micron spacing, and I can do this billions of times a second, and I can put down picoliters of fluid. Think of anything else I might be able to jet? Oh, actually, human cells is true, and we could go into that at another point, but that's not what I'm talking about today, although if someone might get a clue from that. Yes, so we'll go right there in just a moment. Yes, so nano particles and other things. The point is now I have a delivery vehicle for putting other things down as long as they're jettable. Okay, so now I'm into these solutions, but gratefully we figured out a lot about how to jet stuff, and I'll talk about that in just a moment. All right, I wanted to spend a little bit of time. I love these things, like the feather's so cool, but the key item I wanted to highlight is what are people actually doing with this stuff, all right? So these are all the things people are printing today. Skull patches, headphones, almost all hearing aids are actually printed 3D today, almost all, except the really cheap ones. There's crowns, bridges, dentures, implants, a whole bunch of stuff, orthotics. Did you notice her arm? Okay, most people don't, and I find that really intriguing, and I would love to know why, but people don't. I think because it looks like a glove, maybe. I think if she had a glove on the other hand. I don't know. It's really weird. Braces. So we now have entire companies who are making braces to support legs when people are running. Did you happen to know that babies' heads come out a little deformed sometimes? And so there's actually these weird things that basically help the skull form in the right way. I didn't know anything about this, but what's interesting about it is it has to be softer on the inside than it is on the outside. So you're now using structure, honeycombing structures and mechanisms to create differences in how squishable and how, what's called ductility, how much tensile strength is necessary to compress it. This is exactly the same material as this. But, yeah.
How did you like overcome, like, you know, when you're eating and cooling, like how did you vary, like you must have had to vary the powder.
I don't have to vary the powder, which is a really interesting thing. I do vary what I put in the chemistry. So remember, I'm jetting down this fluid, so I now can change the chemistry that I'm doing at these incredibly small dots. And do you remember, like, all of INKJET is all about dots on page, that your eye can't quite see what you did? That's what's going on here. Here's another one, scoliosis braces. I don't know how many people know what old scoliosis braces looked like, but that is a huge improvement, if not a fashion statement in itself. And I'll make a comment about fashion in a moment, which has been really surprising as well. Orthotics blew my mind. Here we have people actually walking across a plate, and we actually measure what happens with their foot. And so HP actually sells something called the Scan Station. We did this with Nike, and we make custom insoles for your foot. Your foot, not somebody else's. Yeah?
Can you make the whole shoes?
Yes. So Nike and HP actually make whole shoes. We make sandals right now as well. They're not branded by us, so I don't remember who's, I think it's Nike's brand on it. But I guess I like to say we're the sole inside. But, but it's amazing. And weirdly enough, we ended up having to have this little toe part. I didn't know this, but so much of your balance is coming from your big toe that turned out having that also padded was a really important part of the orthotics. And you would find this when you were looking at the underlying structure of someone walking. How about this one? This is, if you're going to go have knee surgery, they make a little attachment that goes on your knee. Not anyone's knee, your knee. So when they cut across it, they get a clean area to then splice onto. So it actually is pulled from some CAT scan data to actually produce it. This is actually one of my favorite props. It's also printed 3D. And the cool part about this is what we found from doctors is when they're explaining what they're about to do, it helped them to talk about what it is. You can show any model you want, any x-ray you want, you can show almost anything else, holding something in your hand and saying, this is what's broken and this is what I'm fixing. Huge educational tool, huge. If you do back surgery, most people won't know this, but you don't actually see all the vertebrae when the doctor's working on you. They only see the top of it, typically. So they basically, with this, they can actually see what's wrong with the part, And no amount of advanced modeling or AR, VR, or anything else is going to be the same as holding it in your hand. So I say there's AR, there's VR, and then there's R, physical reality. And so this is actually barcoded because it's for that particular patient. It's actually verified that this is your one, not the other guy we're about to do 30 minutes from now. Actually, that's an interesting point. What surprised me was the economics of this, and I'll talk about the cost and the economics as well. But what surprised me was how expensive an hour of surgery is. And so if you can make it so the doctor gets right the first time, huge improvement both to cost and actually to patient survival. So there's a direct correlation to how long you're in surgery to what your survival rate might be, I guess inverse correlation. Okay, next one is manufacturing. Just want to kind of do this one quickly. I have one of the parts here. It looks like this. What's cool about this is that all the channels have already been built in. So you don't have to add anything to this. It's airtight. All the suction cupping capability, the pneumatics, everything else basically works with this part. You might notice these honeycomb structures. This is the other thing we're starting to see a lot of, is that the design starts to become generative, meaning that we're removing the extra material, but maintaining all the strength of the underlying part. And so things are starting to look a little bit more like nature did it than we did it. And there's something really deep in that. And I don't know who here is out of design, but 3D is a huge opportunity for transformation of design. Both computer-generated design, which I mean by generative design, where you basically let the computer run through a whole bunch of different algorithms to figure out how to get the lightest weight, but the strongest structure. But if you muck around with this one, it's unbelievably strong.
Can I stand on it?
Yeah, I think you can.
You're right.
I had a moment because I had to figure out how much he weighed.
250 pounds.
But let me show you one other. Can anyone guess what this rig is? Okay, they'll tell you.
S3 belongs to FICEP Group, which is a multinational company that constructs machinery for structural steel. So when you see a building or a bridge, all the metal structure was probably made with one of our machines in over 30 countries all over the world. We never considered using 3D printing for production until we saw HP's multi-jet fusion in action. Now we're doing parts which we weren't able to make before. Now we do them in-house, and we have them the next day. The machine that we're building is a paint machine for industrial steel. Once we saw how the parts come out, we noticed how strong and light they were, then we just redesigned the entire machine based on this technology. 40% of the machine is done in 3D now. The robotic arm which holds the paint nozzles. In a traditional machine, this arm is about 1.5 meters high. We were able to reduce it in 3D to 300 millimeters. You can't design it any better than what it is now. And making the parts so small, we were able to save a lot of space, where we were able to add other systems without increasing the floor space that the machine takes up. Just making one part in 3D can help you rethink the entire machine. What HP has done is made us a machine that can not only do the prototypes for us, but also do the final production. This is where it excels, because now we don't have to wait 12 hours to make one part. In 12 hours, we can make 100 parts.
That is about 1 hour. And again, it's because we don't have any limitation X, Y per se, except the size of the bed. Z is our item, and it takes about an hour for that to go through the heating cycles. But what's being used is on manufacturing. Oh yeah, I'm sorry.
How convoluted an internal path can you clear of powder? Right, because some of these have like air passages through it or whatever.
Yeah, so that actually is a good example. I have a really great one where I tried to figure out how the heck the person did it, and they ended up printing a pipe cleaner inside of the element. So they 3D printed their own pipe cleaner, and then they pulled on it to pull it out. Other people use chains. And so I've been amazed at what people have come up with as clever ideas for how to deal with pulling stuff out. And oh my gosh, that's cool. I have another one here, but I won't show it. Jigs, effectors, thermal modes. Oh, people are using these for molds. So if you go to injected molded plastic, just having a mold very, very fast. There's a lot of these. I could spend so much time here. If you've ever been stuck out in nowhere land and you need to make something, having all the parts, if you're into mining. But what I want to do is talk a little bit about what's going on in automotive and aeronautics. Now, there's a whole lot of regulations here. So one of the items is what can you bring in, but there's a little knob. I don't know if you can see it. You see them with a trim knob right here? That's what all that stuff up there is for. This is what it's like when it comes out of 3D. It's 2 parts. Because we don't have to assemble. We can print the whole thing already assembled. Same thing here. This is my badge holder. And it spins around here as well. And if you look at this, you were like, how could that come out that tight? There's no assembly. All right? And again, it's because we can print it already pre-assembled, we basically use a sandblaster or an air to blow out any excess powder. And there's lots of other techniques. Someone mentioned about intake or manifolds. Intake manifolds we know how to do. Exhaust manifolds, wait till metal. Just a reminder that they run about 1,000 degrees, so melts most plastic. But it works quite well for the works quite well for the for an intake manifold. We didn't print these gaskets, so we're still using stuff with gaskets. That'll be the next thing, is get rid of having to add another material. We can just do the chemistry and make the adaptation right there. Last part I want to talk about was consumer goods. So here's what I think is fundamentally about to change. And when I wrote the abstract for this talk, it was like, okay, that's a little too bold to say it's the next industrial revolution. I get it. And you could say whether it's the third or the fourth, I don't care. I do think it's transformative. The reason that I think it's transformative is right now the model on almost anything made in the consumer world would be to print, 1 million of these or 100,000 of these things. This is just a snap for a backpack. But you don't have to, and you don't have to store it anymore. So if you're missing your dishwasher part and you need a replacement of that dishwasher part, you just reprint it. So just like books are now available on Amazon on just-in-time printing, same thing's going to happen here with parts. So storage of parts, which has certainly been going on, and discarding of parts, I believe will go away, and you'll see more onshore manufacturing, localized manufacturing. Because there's no reason to ship it all the way over, get low-cost labor, and bring it all the way back. Because the labor was primarily in assembly. And guess what? You don't have to do assembly anymore. This will change the economic nature of manufacturing. So what's changing?
The big problem with that, you can make all the mechanical parts, but you got to package with electronics.
Yeah, so let's do that next. Yeah, and I have to be careful because I said I would be finished in time, right? But I could go through things. I'll cut through a couple of these. This is what a mold looks like for those who have never seen what injected molded plastic looks like. But rather than spending thousands of dollars or weeks making a mold, you just print the part. You don't even bother with the rest of that. And on this particular part, the break even between 3D printing and doing injected molded parts is 120,000 parts. So when we shipped our printers, 50% of the plastic parts in our printer are made by the printer. It was economically better to do that. It also made a good PR story. But it's absolutely was economically better. So what's changing is we're moving from mass production to mass customization, from overseas production to local and distributed production, and from storing parts to storing files. Someone will figure out how to be the iTunes of this marketplace. So the aerogenerative design is here. I showed a couple of samples here. I'm just cutting forward. But how are you guys with your CAD tools? Think that that knows how to do anything for 3D printing? It knows all about geometry. What about the stuff inside of it? Is it hollow? Is it filled? Is it strong? Is it flexible? How's that for your CAD tool right now? Can you get it? Maybe if you get the Autodesk add-on, but sort of. What if you want to vary it across the structure? So I'm going to show you some weird things here. So fabric is now starting to be printed. Alex made this one, and Ji Wang volunteered to show it. I had to bribe her. But so it's not a great hat yet, but you can probably guess that this is where things are going now. Of being able to build these unbelievably intricate structures in the back of the material to make it fold and bend and flow. So Thor's hammer to the feather. My question for you on the CAD design is, how would you describe this feather? How would you talk about it? Would you talk about it in terms of the underlying material? Would you talk about it in terms of its thickness of the elements? Would you be running finite element analysis across it? No. We need a whole nother language to start talking about things like it should feel like snakeskin. We have a whole problem, and by the way, this is me pitching to all of the undergrads and grads. If you're looking for your PhD thesis and haven't figured it out yet, boy, do I have a few for you. I mean, what's cool about snakeskin, if you haven't noticed it, it's really smooth in one area and it kind of bristles up on the other side of it. I'll show you something here in just a moment that's like that. This was actually, I did this for Chris. Printed tambourine. What we were really intrigued by, and this was also done by Mary Baker in my lab, was how thin the top could be. And there's no assembly. And she actually did make a musical score where she had one of these, and she had something that whistled, and then she had this cool thing. And honestly, I thought about your activities, and I'm sitting there going, and if you look at this, it starts to have the feel of the snakeskin, where it's flowing in one way and not in the other. And you can imagine that a dress like this or other elements happens. There's so much cool stuff here, but what I want to talk about this VOXEL, so your question, these VOXELs are about 70 by 70 by 100 microns. Now, they can be smaller. I'm just saying that's what we're doing today. So we are able to manipulate the properties at this level of every single one. Okay, so if you're designing your software, do you want to be talking about the property of every single voxel? Or do you want that to be a discretization of some analog function? Probably you want to do it functionally with the discretization of an analog function. So I'm going to give a quick one more video, and then I'll try to wrap up here in a moment.
At each volumetric pixel, or voxel, HP's transforming agents could control surface texture, wear, and friction. HP transforming agents could control the translucency of each voxel. HP transforming agents could allow one to optimize the strength and stiffness in portions of a part, and to print elastic voxels in other portions of the part. HP transforming agents could be used to change the conductivity of certain voxels. HP transforming agents could also be used to enable the printing of new advanced materials, or enable emulating different materials at each voxel.
So you notice he says may all the time. That's because this was an external marketing video. And what we have in our lab is stuff that's doing all of this. We just don't know how to productize it yet. And it's totally cool to work on. Variable ductility, I don't have the language to describe it. I don't know how to talk about what a feather does. And yet I can do the behavior of that. This is a huge problem. Conductivity, we actually did show a Wheatstone bridge for strain gauges. We've been doing some stuff for figuring out how much pressure is on a particular part. You can run the traces, that's fine. The next part is how do you get some other electronics inside of it so it's advertising out and all stuff that's going on. I'm just saying, again, great area for folks to be working on. Okay, so I asked the question, what is this thing? I'll give you a clue. This is a really big version of it. Oh, yeah, that's good.
Looks like a monolith.
Okay, I used it trying to explain to one of my daughters how big the nucleus of a cell is. This is Anthony McClellan's white blood cell, blown up because we had it rotating on a spit, so there are ways to hold a cell and spin it. So we took his cell and then blew it up, modeled it, and that's why it's irregular shaped, because actually white blood cells really are irregular shaped. And they're very cool. Most of the time you see them, they're squished underneath a slide. So this is without it being squished. We ran it through a microfluidic chamber, and we're actually watching it. You can get really high-speed cameras now, and once you can freeze it, you can rotate it. But what was cool was, if you ever see it under a microscope, it looks like the nucleus is really small, but it's not. It occupies almost the whole space of this white blood cell. So my purpose of showing you this, and if someone is actually very good at this, they probably can tell whether it's an eosinophil or one of the others. But my purpose of showing you this is I also think it's art. So there's something different happening. Now he wanted his personalized art. And again, this is the guy who's printing Thor's hammer and other stuff. So I can't really tell what other body parts he'll be printing. But it's exciting what happens. And that level of creativity and play is unbelievably necessary in this marketplace right now. Okay, just finishing up. We do print in stainless steel now, 316L, for those who care. We do make metal jet printers. They're not released yet on the market, but we are using them. And we're getting parts off of them. Yield's not quite what I want, so we can't release them yet. But we are doing that in partnership with major suppliers right now, just like we did on the prior ones. So my real point of this whole thing is disruption starts quietly. And when it's time for steam engines, it's steam engines everywhere. This is a great quote that's attributed to James Watt, 1765. And it also happened to Thomas Edison when he was running to the patent office because 5 other people were running to the patent office at the same time. When it's time for the invention to come about, it really is co-invention. It's not stealing. It actually just all happens because all the precursor inventions have now happened, and it's possible to do. That's what happens when you have inkjet heads that can put down 30 million drops per inch. That's what's going on when you now have enough of the elastomer science and modeling to occur. Once someone shows a way, it changes what happens in the marketplace. And that's essentially when you know you're there is when the compelling applications start to show. So the technology comes right after that. And so some key observations. Innovation doesn't happen alone. It is all about the ecosystem. We know this. It's about the applications. It's almost never about the technology, which I always want to tell you about. And I'm happy to tell you all the chemistry we do, but it's really about the applications and who will use it. Very frustrating, but it's true. And then it takes forever for an overnight success. It's always a series of small innovations. This is a small portion of my team. They're very happy because they got a new tensile tester and they're breaking stuff. My team seems to love to break things. But we're missing the needed science, from material science to big data modeling to smart 3D printed devices to entirely new languages to describe the parts. It's an entirely new wave of manufacturing coming at us, and it is a huge opportunity for multidisciplinary people to bridge between I should look in here. Biology, chemistry, metrology, another chemist, although he doesn't think he's the same as the other chemist. Color scientist. It's an amazing multidisciplinary group. So innovation is all about culture. And when you join a company or go anywhere, look at how they work and what you valued. I highly encourage you to be thinking multidisciplinary. And with that, our item is always keep reinventing, and so metal's next. Thank you. If you'll turn up the house lights. Yep. So I can take a couple of questions. Yep, and I'll be around after.
I'm going to ask the students first if that works. Okay, you go first.
Thank you. I'm wondering how you address the issue of anisotropy in different directions when you do 3D printing.
So it's a great question. we tend to address this a couple of different ways. Because of the underlying powders, we don't typically have a problem on the surface. We can use coronas to change the wettability of that surface. But generally, that's not a problem due to the material we're working with right now. But as we grow to other materials, you are on the hard problem that we have. And for that, you get a 3D part. Does that motivate anyone else?
All right, visitors.
If you wanted to print a cushy doll, and I'm from continuum mechanics, so I'm talking about large deformations and things like that.
Yep.
Do you see that the needs will be having the theory to solve that? Because it's really
Oh,
very
that's a deep
difficult,
question.
optimization problem. We don't know what the microstructure
Yeah,
would
so-
be like to feel cushy.
Yeah, so where's my part of cushiness? Yeah, this one, cushy. I don't want to be flippant with the answer because it's actually a really deep question, which is engineering is about using limitations to solve impossible problems. Because if you did them in full, they're typically impossible. You have to get the science to get that right. And sometimes we don't know what that science is. In engineering, we can make a constraint that I'm only making it this big. And now it's sort of solvable, or it could be solvable. The expression of, do I have a model for cushiness, that's really, really tough, and we don't. This is the short answer to that question. So I admit we don't know. Do I think we can probably bound it with some quantums around what feels like cushiness? Is it as cushy as tissue paper? Is it compressible enough like an airbag? We can probably start getting to that type of level, even if we can't quite get the science right. So I think that's where we are right now. Now, your question's a lot deeper than that, and actually you'll get a part 2. But I don't have a way to express the actual formula for that. But do we need to? The answer is yes, but I think we can do shortcuts until then. Yeah.
Hi. I have a brief question. So I was wondering, you are printing everything, and this is, sounds awesome. How do you recycle? Is it possible to recycle in local for every customer rather than going to the company and ask for any other additional machine? And then how does it cost and how does it impact on the manufacturing itself?
Yeah, so HP as a company is highly tied to all of our material is fully recycled. So we have a zero landfill-based policy on stuff. So that's the policy. Now the reality is we're not quite there yet with 3D. The material can be reground and reused, but again, this ties to the material that we use. So right now we're in a polyamide 12, so nylon 12. And if you know anything about the material, it can be recycled. It's just not the best recycling item. So where we are going next will be into these biodegradable materials as well. So you can imagine that we have an entirely broad set of materials coming in, and we've made an open materials platform allowing all these lovely chemical companies to help build materials to go into our devices. It's a great question. It's absolutely our goal. It's part of how we do everything else, including everything from circuit boards to anything else. But yeah, it's not where we are right now.
Can you foresee the day in which...
Yes, I can totally see that.
Okay.
Yeah, no, I'm committed to that. That's part of why I work for the company I do. It's the right question.
Thank you.
Oh, do you want one?
Thank you.
Okay. Yeah.
Here.
Oh, sorry.
Front row,
Yeah.
front row.
The way I'm seeing 3D printing is that you're basically building it from the ground up, and there's like whatever the previous layer is in the middle. It's made by the 3D printer. Are you exploring any ideas of actually printing around an object?
Yes, we do. So conformal manufacturing is what that's typically referred to as. Absolutely. So if you're going to put electronics in the middle of these things, the normal problem is, will it tolerate the heat? And so a lot of what we have to work on is what can you put in the middle of something that you're jetting a whole bunch of water on and heat on and other things. But yes, you can absolutely do conformal manufacturing. Not with our printer right now, anyone who was buying one. They're $250,000, so I don't think you will, but if you were.
The person behind, yeah, you.
Oh, okay, here.
So I recently heard something about 3D printing technology implemented in the biological field.
Yeah.
3D printing parts that mimic
Yeah.
certain tissues.
Yeah.
So that the surgeons will be able to do like mimical surgery before the actual
Yeah.
surgery to minimize the
Yeah.
time and uncertainties that happen into the actual surgery. And due to the like flexibility you have with HP INKJET 3D printing, and I wonder if HP is thinking any. I know you guys are dealing with metal right now, but
The other half of my lab is doing life sciences and bio. So that doesn't mean I can tell you anything about what we're doing. But yes, and then we do think that biomimicry is a really important part, and then re-engineered materials is the other side of that. All of that's true. Someone asked me whether one of the things I'm playing with was a scaffold for other stuff. I don't know, maybe. But you'll have to sort of invite me back in another round, and we'll see what we say next time. So sorry, I can't answer your question, is what that really came down to.
Yeah.
Yeah.
It's really compelling to hear you talk about functionalizing as you go and changing material properties in polymers.
I don't think I said I was functionalizing the end of the polymers, but that's true.
Well, you're adding changing properties as you go.
Yes, I am. So it's likely orientation and other things will all come from functionalization. That's true.
So you've chosen my favorite steel in 316L, but it's not real high. Have you thought about how to functionalize and change the metal alloys as you go up?
Yes, so digital alloying is absolutely possible with this, and in some of the things we're doing, we are jetting metal nanoparticles into material that allows us to modify it, but it's not in our product at this point.
Are you flowing gases?
I won't talk about, so yes, we do work in gases. I can answer that. Yes, we work in gases. I can't start telling you what we're doing in forming gases or other things. That's an interesting element, that the way we do our metal work, how many people use like a kiln and pottery? Any artists in here? Awesome. So 3D printing for metal is that moment where you have a beautiful part, it's come out so gorgeous, and you take it over into the oven, the kiln, and it blows up on you occasionally. So that's where we are right now, which is the yield from the oven, from the kiln. It's just like in pottery. If you get the glaze wrong, you got it too thick, you get a crack, you get water in it, it breaks. Same thing. So we're still working, and I'll use this for the gas conversation. If you're trying to get anything you put in out, you typically have to have something that will bind to it and get it out of there. And so very common gases are used there. I think that was enough that it gives you an answer to your question.
Eric?
Yeah.
So for the metals,
can you pass this back?
could you talk about that a little more?
Yeah, what would you like to know?
Yeah, just in terms of the process, how the metal gets jetted and then what the...
We don't jet the metal.
Process.
Well, we do, well, let's see, I can't say that. We do,
Just what are the
sometimes we jet metal, but in this particular case, we deal with a metal powder. So just like the plastic. So it's, someone said rising from the bed, it actually sinks. So the layer is always at the same level. So it sinks into the bed. We lay out a layer of metal powder, and then we jet onto the metal powder something. I think it was disclosed. One of them was disclosed, which was a latex binder. And then that will hold together what's called a green part. And then the green, so we do this layer by layer by layer, and then you take the green part over to typically the kiln. And so you can think about it like clay, right? You have a lot of water that's kind of in it and holding it together.
Right.
And then you hope, as it goes to the other thing, that when the water comes out, the stuff stays together. Now, there's a lot we do behind that, and for anyone who has spent 3.5 years trying to get your process right for what you're generating, you'll know what I'm talking about, that the process is everything. Getting that recipe just right is really, really important.
So in the metal, you've got a two-stage, because of the heat you have to apply to the metal
yeah,
is
so
high, you've got to have the kiln.
Yeah, you could, and I know we're out of time.
Okay.
Okay, you could theoretically try, let's see, how do I answer this one? The short answer is we are doing it with a two-stage in terms of what we've publicly announced. Because just think about when most metals are forming, it's about 1,000 degrees C, so you're not really wanting to have everything operating at that. Whereas in the powder beds, I can work at 100 degrees C just fine and be perfectly capable of getting a decent part out of it. And by the way, if you ever work with clay, it's actually warm, if you notice. It's doing something, right? We're doing that too. Metal's all weird, but when you're jetting in, you can jet in metals and other things, but let me keep it simple for this one. The simple metal parts are mostly bound latex that you then remove the latex out.
Right.
All right, I mean, it's good call one faculty member here.
Yeah, I could throw something.
Great.
Come see.
Do you have made sensing voxels?
Let's see. The short answer is yes. So the Wheatstone Bridge is the easiest one I can talk about, which is just...
I mean on the voxel side.
Yeah, so on the voxel size, some material, and if you know your chemistry, you'll know that one of them I mentioned already, happens to have some piezo effects. So you can get some elements around capacitive nature. There's some other inductive elements. You can do some other things there. Was that vague enough? Yeah. Okay. So the short answer is yes, but it's not what we ship. And again, for those who don't know, the only reason I'm cagey on some of this stuff is I can't keep all the patents if I tell you how to do it before I got them filed. So, anyway.
Matt?
Can I ask a question about the energy input? So
Yeah.
this is going to be the next manufacturing wave.
Yeah.
Is there a savings to be done when you're doing certain parts or certain materials? Or?
Yeah, that's, so short answer is we have lots of studies that would say yes, but it comes down to how many are you making and what your economies of scales are. There's a reason why in the first industrial revolution, depends on when you want to count it, the steam engine basically allowed you to move your plants away from water power sources, right? Because water was your mechanism powering everything, so now you had steam engines to do it. The energy you're putting in is a real core element, and I have a very good colleague. He's a senior fellow at HP and one of the engineers at the Academy of Sciences. Amazing fellow, and he calls everything joules, meaning everything's the joule that you want, but he means it Joules, which is it's always going to come down to energy when you're done. That'll be the unit. It won't be how much one part cost you, it's the joules that it took to make it and the joules it took to recycle it. Total cost. That's where we're going. With that, I have to stop, but I will be around, and I just wanted to both thank you for giving me the opportunity to talk about it, and I hope it was enjoyable.